Um, so a couple of things this evening. The first, you can see I've dedicated this presentation to a gentleman called Arthur Erland. You may or may not have heard of Arthur Erland, but Arthur was the president of the Hertfordshire Natural History Society back in 1938 and 39. And like me, he was a chalk micropaleontologist. Well, he was a micropaleontologist. So I think it was, I suppose I can look upon him as being a bit of a predecessor. What Arthur is, one of the things he's famous for is that he worked in conjunction with another gentleman and called Heron Allen, and every Christmas for about 25 years, he used to make slides, microfossil slides like this. You can see it says the Erland collection. And he used to send slides like this to his colleague, Heron Allen. And every Christmas, here's one, here's the Edward Heron Allen received this in Christmas 1909. There are similar ones. All this collection is in the Natural History Museum. But these two gentlemen worked together. Heron Allen was a remarkable character, worked on all manner of things. He translated Persian, he was a solicitor, he made violins, and he also was a micropaleontologist, as opposed to Arthur Erland, who was worked for the post office, and in his spare time fitted in his natural history interests. The two were almost inseparable in their work for about 25 years. And then in the 1930s, they fell out, never to be reunited. There are various stories why this was, but the main story is that it came down to the affections of a young lady. So that's as much as I know. I'm not going to go into details, but that is part of the background on Arthur Erland. But he's not the subject of the talk. The subject of the talk of the Gerald Salisbury lecture tonight is, I've called it Still Living in Hertfordshire. And I have a minor apology. When we set this, when I suggested the title for tonight's talk to David Utting, he thought living in Hertfordshire for the last 100 million years sounded really good. So yes, let's go ahead and do it. And it was only afterwards, when I was checking my records, that I realized that I actually gave a talk of that title to the Natural History Society back in 2015. So I've been looking at the presentation, I've updated it, and we are still living in Hertfordshire for the last, or over the last 100 million years. And hopefully,
hold it to your ear, because it's as loud as I can get it on, because it's phone.
Oh, I've got the competition. Okay, I mean, basically, in the last few weeks, I've been able to update this talk, and hopefully, those people who heard it previously, maybe it'll be something new, and those people who've not heard it before, well, okay, you're in for a treat. We've got 100 million years to get through in about 50 minutes, so 2 million years a minute. Let's see how we do. First of all, when are we talking about? I mean, fortunately, I've inherited one of these TARDIS things. We'll be starting off at around about 100 million years, traveling up to around about the end of the deposition of the chalk and the early part of the tertiary succession, and we'll be whizzing through to the up towards the present day, stopping off at a couple of places on the way. Just to give some idea, we'll be talking a lot about the chalk initially. I put this in because if we take a line at the base here, which is around about 100 million years, this is just an idea of increases in sea level. The time we're interested in, you'll see here, it says Hertfordshire chalk, and we're mainly interested in this lower half of the diagram, if you like. A couple of things show up on here. There's a note here, it says change from shell detrital chalk to smooth chalk. Not all chalk is the same. So that is important. It's one of the things that you may pick up as we go through. And then there's also a note here saying change from smooth to nodular chalks, and volcanogenic Mars. So Mars coming from volcanoes. Even that was going on when we were getting the chalk deposited. So where are we talking about? Let's have a look at the globe around about 100 million years. This is 94 million years ago. Let's put our TARDIS, there we are, we've got our time machine sitting over the southern UK. And what we're looking at here, first thing you might notice, there are no ice caps. During the late Cretaceous, there are some indications there may have been occasional ice at the poles, but there were no permanent ice caps whatsoever. There was complete melt, ice melt into the oceans. So that partly resulted in high sea levels and major flooding onto the continental shelf areas. So if we look, there's the UK smack in the middle. You'll see that large parts of Europe were basically flooded. The continental shelf was underwater. Similarly, parts of North Africa through into large parts of Libya and surrounding areas were underwater. Likewise, there was the major Western Seaway through North America. The Atlantic was just beginning to open up. It had started splitting down in the lower Cretaceous, but we're into the late Cretaceous, so it's really beginning to get going. And this other ocean here, the Tethys Ocean, which we have no remnants of really at all nowadays, it's completely gone. Tethys was closing up. And as part of that, it's a note there saying, check where India is. India was still attached to Madagascar. Part of this major supercontinent down in the South Gondwanaland was splitting, and India was about to head off at a rapid rate of centimeters per year until it smashed into the southern part of Asia. So there's a lot going on, and we're just part of it, sitting up here on the edge of the North Atlantic as it opens. If we look at some of the older maps of Northern Europe in our area, this is by a guy called Peter Ziegler back in 1990, it looks as if there wasn't a great deal going on across Europe. It all looks pretty much the same. There was a few things going on down in central Germany and central Europe, some highlands, but it looks pretty well flooded. But that is not really the case. There were a lot of changes, with changes in sea level, which impacted on the paleogeography of the time. So if we go back to around about 100 million years, parts of England at that time hadn't been submerged. We were still seeing the rising sea levels beginning to encroach through the Anglo-Paris Basin here, which was opening up through the North Sea Basin. Just out of interest, you might want to note that Spain was actually facing the wrong direction altogether, from what we know, and was about to rotate round, swinging round to the left along this big fault system that comes through what is now the Mediterranean. So again, a lot of movement going on. And if we push up into around about 75 million years, those increasing sea levels through time had really begun to flood right the way across the European continental shelf. So it's a time when, despite the fact that we tend to assume that white chalk with flint all looks pretty much the same, there are a lot of changes going on. Now, one of the things I want to pick up that you have to be aware of, this is just to show some of the structural controls that we've got going on through this late Cretaceous period that we're talking about. Here's the UK sitting on this sort of extra little bit of Europe on the edge of the opening Atlantic. And the Atlantic is just beginning to start spreading. Spain is beginning to rotate along this fracture zone through here. And because of that, we get things like volcanic activity going on. So if we look at another map, same area, same sort of time, we can see all this rifting going on through here. So there will be volcanics associated with this right the way through into the central Atlantic. Now, it got mentioned before we started that the Icelandic volcano back in 2010 managed to send loads of ash across into Central Europe. Well, the same thing happened during the late Cretaceous, the period that we're talking about, around about, say, 75 to 100 million years ago. And following the same sort of Coriolis effect that we see in the atmospheric circulation today, the same thing happened in the deposition of the chalk. And you can say, well, do we see any evidence of this? Well, we do, because this is Royston. There's a section just sort of central Royston. These clay seams running through here, marked with the red arrows. If you check the geochemistry of these clay seams, the trace elements that are in there are all typical, and the clay minerals that are in there are typical of the sort of clays that we'd expect to see generated by volcanic activity along a mid-oceanic ridge. So as the Atlantic is beginning to open and is beginning to throw out clouds of volcanic dust, that is then circulating the atmosphere and landing on that continental shelf while normal chalk deposition is going on, but it's punctuating those. And because it's a volcanic ash, it's a snapshot in time. And we can find the same ash with the same geochemistry. Each of these ashes can be fingerprinted by its trace element geochemistry. And we can find exactly the same ashes in the Saxony Basin in Germany, for example. So it's remarkable that we have these controls. So this is just getting us started. We are starting our 100 million year story. And I just want to paint the picture. We've come to this situation 100 million years ago. Most of Europe is beginning to flood. We've got open seas covering most of the continent and the continental shelf, except for those high areas like Scandinavia, a few other areas like the Scottish Highlands, Shetland and the Lake District, the old Paleozoic rocks of those areas, and Wales and Ireland, and then the granite areas of Dartmoor into Cornwall. Those areas are still standing proud above sea level, but they are progressively flooding. You can see that there's a deep submarine trough down what is now the North Sea. So even in late Cretaceous times, that it's a failed graben area, a failed rift, and that was filling with sediment throughout this time. Hertfordshire, if we put that little red arrow where Hertfordshire should be, it's totally submerged. Probably sea levels up around about 150 meters higher than they are today, not just simply because of that melted ice and no polar ice caps, but because of the amount of thermal activity with the rifting in the Atlantic and other ocean areas. We get what we call thermal doming. So the ocean floor is pushing up. And because the ocean floor is pushing up, it's actually reducing the amount of volume that can be held in the oceans. So the sea level spills over onto the continental shelf and we get this increase in sea level. So that's where Hertfordshire's sitting. So do we actually see examples of this? Well, we do. This is Pitstone Quarry, right on the Hertfordshire-Buckinghamshire border. It's one of those strange places where we're actually standing on the top of Pitstone Hill here, looking out over what is Quarry 2, or the flooded part of Quarry 2 at Pitstone. And in the distance, just if you like, the middle foreground there, you can see what used to be Quarry 3, which is now called College Lake. And in those two quarries, when we look at the geology, they have almost a complete section of what would have been deposited during the time when we have, if you like, deep marine circulation, open marine setting. We don't necessarily have mosasaurs at this time, no evidence in this area, but certainly we have plenty of ammonites and plenty of other fossil material in those sections, particularly that came out of the quarries at Pitstone, particularly College Lake, before it was completely, when it was taken over as a bird reserve. And here's the section. So the lower half of this geological column is the section that's in College Lake now, or Quarry 3, as it was. And then the upper part is what is still preserved in Quarry 2. Quarry 2 is not so easy to get into. It's still being worked for chalk to a limited degree. So access is not particularly easy nowadays. But if we look at the fossils that we get in there, we see plenty of ammonites. There are masses of ammonites in there, bivalves, things called Inoceremus, which are particularly common in the late Cretaceous chalk sections. There are these strange looking things at the bottom, but they are big sponges. The lower chalk is renowned for the chalk sponges called Exanthesis labrosus. They're really quite major, and a lot of the limestones that occur through these sequences, you get sponges throughout. So it's very fossiliferous, and implied that the sea floor was well oxygenated. There's lots of burrowing in place. We see lots of trace fossils in the burrows, so we know that the sea floor was oxygenated. So that's the situation that went on through from around about 100 million years up to probably around about 97 million years. So for the first 3 million years we've had. Then we come up to the section at the end of the lower chalk, or the end of the Cenomanian stage. And this is a section, again, still in Quarry 2 at Pitstone. This is the sequence that's recorded there. Probably one of the most important parts of the sequence is the lower part here, and it's called the Plenus Marls. Although it's called marl, and it is an alternation of dark marls and limestones. There are 4 of each. There are eight beds through here, and they are really quite unusual. They form the lower part of the bluff in this section, and then those are capped by what's called the Melbourne Rock from Melbourne in Cambridgeshire, and that's really this yellowy section that's coming up in the upper part of the bluff. So they are present. The Plenus Marls are very rarely exposed. This quarry is really important because it's to my knowledge, one of the only onshore exposures of this sequence in England at all. You can find the same sequence down on the south coast of Eastbourne, some places on the Isle of Wight, but in terms of finding it onshore, it's almost impossible. So it's important that we keep sites like this open. And why is it important? Why does this section really make a big change? Well, all those organisms that we were seeing in the lower chalk, they died. We see fantastic, if you like, complete wipeout of the fauna. So we've got to ask, what was going on during the deposition of these clays, these marls, to actually really take out all those animals through the water column. It's really quite important that we understand this. And just to show what's happening, this is not just an event that we see in England. This is a global anoxic event. We're seeing low oxygen levels in terms of across the whole of the globe in the oceanic environment. And this results in the deposition of clays which are rich in carbon-13. And that excursion in the, if you like, the carbon-13 excursion, you can see it here on the Isle of Wight, and you can see it here on the Dover section where it really kicks off. And we've got exactly the same situation on the section that we have at Pitstone. If you ran samples looking at the carbon isotopes through Pitstone, you would see exactly the same sort of event. Paleo temperatures were getting really high at this time. And because of the, there was also restricted circulation in the ocean basins. And because of that, the oceans became stratified. And if you look in this lower diagram, you'll see a level that's called the oxygen minimum zone. And what happened, that oxygen minimum zone, as sea levels rose, the minimum zone rose with it and eventually flooded into the Anglo-Paris Basin, bringing that low oxygen level into the Anglo-Paris Basin. And all the fauna, the ammonites, the other organisms, particularly on the sea floor, were just wiped out. So sea level rise pushes the oxygen minimum zone across the continental shelf. And we see these black clay stones right the way across through Europe, through North America, through North Africa, down through West Africa and offshore. So it is a major oceanic event. The oceans recover, and as we move into the increased circulation, allowing the oceans to recover, we move on into, although this is the campaigning, which is up to 75 million years, what we're going to be talking about is just a progression up through the 90 million years. Sea levels continue to rise. They just keep moving up over that sort of 90 to 75 million years there. Scandinavia is still land. So are the Scottish Highlands, just about. A few other areas in Scotland, maybe the Lake District, possibly Wales. Ireland is completely flooded. And Hertfordshire has completely been taken out as well. But it's interesting that these sea level rises, it's not just one continuous rise in sea level, it's punctuated by periods when sea level fell, sea level stood still for quite a long time. And that's one of the important things in our area. Around about 95, 96 million years ago, we had a period when the sea levels were pretty stabilized. They rose and fell, but on a short-term basis. And they probably halted for a time. This allowed the seafloor to be burrowed by worms and crustaceans like shrimps and crabs. And the burrows even had time to become hardened and to become mineralized. And we see that in a particular bed of rock. It's what we call the chalk rock. And if we look at the chalk, this is, although it's just outside our area in Hertfordshire, this is at Kensworth Quarry up on the Dunstable Downs. If we look at the chalk rock there, you can see these green layered nodules with brown layers to them. This is layers of what we call glauconite, which is an iron mineral, and calcium phosphate, which is the brown mineral, which are forming these nodules within the chalk sediment. Here's a nice solitary coral sitting here. And then between the nodules, this whiter chalk would have been softer. And these are burrows, which have been burrowed through by potentially crustaceans predominantly. And you can see them through here. And it's very, very rare to find any sort of evidence of these, but it's quite amazing how widespread this particular type of rock is. We can find it. This is bringing us into Hertfordshire. This is Baldock. When they were building the Baldock bypass, I was able to get access to that. Here again, we can see those green stained minerals in the nodules. We can see the burrows running between the nodules. So this is a very widespread event across through the Chiltern area. And in fact, bringing it a little bit sort closer for some people. Those of you who know Hill End near to Hitchin, there is a chalk pit at Hitch Wood. And back in 2018, working in conjunction with Herts County Council and North Herts District Sound Council, we've re-excavated the chalk rock section at Hitch Wood. For those of you who know him, this is Jack Doyle, who has been visiting the Hitchwood section since 1954. So Jack knows a damn sight more about it than I do. But Jack goes up with his bucket and spade and collects the chalk to go onto his rhubarb every year. But it's well worth a visit. And this is a group from the Hertfordshire Geological Society cleaning back the vegetation, doing some geoconservation work on the site. So we have these exposures available that people can look at across the county. As we move slightly younger in the chalk, and this is just, when I say it's just on top of the chalk rock is just below the floor of this quarry. This is right in the west of the county, Springfield Quarry across at Flaundon. You can pick up just this orange layer coming through here. This is another one of those hard ground surfaces. And if you look carefully, the flint bands, as well as the orange surface, are actually curved. There is a bit of a bend to them. They're folded. And there are folds running through the chalk, which occurred later, and I'll come on to a little bit later in the talk. So we're seeing chalk with flint come in. This is the first time we've had real good regular flints deposited. And this is Redbourne Quarry, same age chalk, sitting across at St. Albans. Not quite so easy to get into Redbourne because the Veolia have got a chemical processing plant sitting in the front of the quarry, but it's worth a visit. There is actually an information board in there, which seems ridiculous because nobody ever goes in. But the two quarries, there's Springview Quarry at Flaundon in the west of the county, and this is Redbourne, and we're seeing some variations in the sequence, but the two can be correlated quite well. And this comes on.
Haydon, sorry, can you just sorry to interrupt you.
Sure.
A couple of people just queried whether I think having problems hearing. You're certainly coming across clearly enough on mine, but I just wondered whether you might be able to up the input volume.
I'm not sure. I've had this issue once before, and I'm not sure that I can raise the volume any more than I've got it.
Yeah, I thought that was probably going to be the case, but I was just checking.
So
okay.
I will try to make sure that I'm pretty close to the microphone.
Brilliant. Thanks, Haydon.
Okay, thanks, Peter. Yeah, let's just go back to the previous slide. There we go. I made reference to the fact that the Geological Survey has been mapping through the Chilterns, predominantly on behalf of the Environment Agency, but also for Thames Water and Veolia, or Affinity as it now is. They started looking at the Misbourne, they've worked through the Chest, the Gade, the Verd, and they're now working across eastwards onto the Rib and the Ash and the Storm. So this work will be going on over the next 2-3 years, and the information is beginning to get published. One of the things they've already established, and I made mention of this, is that the chalk isn't flat lying. We knew it was dipping into the center of the London Basin and forming the Chilterns, forming the outer edge of the northern part of the London Basin. But in fact, there are a series of folds that run almost parallel to the line of the Chilterns within the chalk. They're very low angle, very low amplitude folds, but the chalk was being folded, and we probably have to make reference at some stage as to when that took place. So we'll come on to that as we whiz through. And then we come up to probably the youngest chalk that we see in Hertfordshire. This is at Codycut Quarry in central Hertfordshire, And the chalk there is around about 87 to 88 million years old. Chalk deposition would go on for another 20 million years. But we don't see that any longer in Hertfordshire. It was probably deposited, but it was then eroded, and we have to look at when that took place. But the chalk, when this was being deposited, again, it was being burrowed. It was very well oxygenated. We've got sponges again, we've got ammonites, and we've got lots of the typical Hertfordshire echinoid micrasta. And this is the typical micrasta chalk that we see in Hertfordshire. So that's the youngest chalk we get. So what happened? Well, there was a paper published back in 2018 by Brian Lovell, who is a good Hertfordshire geologist and ex-president of the Geological Society, and Professor Andy Gale. And Andy's been looking at some of the sections across the whole of Southeast England. And they came to the conclusion that what was to become the hotspot that forms Iceland today underneath the Atlantic was just beginning. The continental shelf was migrating over it. And as the continental shelf migrated over that hotspot, it domed. You got thermal uplift. And this uplift is marked on here. And because of that uplift, the chalk becomes eroded. And that is critical to our story, because what we find in Hertfordshire is this layer. And this layer represents the top, if you like, the youngest chalk we see. This is at Harefield Chalk Pit, right over in the Colne Valley. And you can see that the chalk there has been burrowed, all these burrows going in. We're not even sure what animal it was that created these burrows. But the boundary between the chalk here at Harefield and effectively this part of the Upnor Formation, because we don't see the Thanet Formation here, is eroding down to around about that level that we see at Codicot, maybe around about chalk of 86 million years old. And we've got a 30 million year time gap represented by this level in Hertfordshire at Harefield. So that's the end of our chalk story, because the 20 million years worth of chalk that was probably deposited in the region between 86 million years and 66 million years has been eroded away. But it did provide us with an awful lot of flint. So let's see where we're going next. We've got our time machine. We're going to move very quickly up. We have at the end of the Cretaceous, the end of the chalk. A lot of people like to think that we had an asteroid which wiped out the dinosaurs. It's very nice. There's an awful lot going on at the end of the Cretaceous. Yes, there was almost certainly an asteroid, but whether that was the total case that it brought everything to a halt is another matter. We know that there was awful lot of volcanism going on as well. So we've moved up into that section sitting on top of the chalk. What was going on around about 57 million years ago. We're right at the end of the period called the Late Paleocene. These are the first deposits we see in Hertfordshire, back in our area down here. And we're up around about 60 million years ago. We've leapt forward a bit, and this is the level that we see. All the flint that was eroded out, we see packed up on top of the chalk here. And this is part of the Upnor Formation that we get preserved in this area. And all that burrowing was going on. We're not quite sure what the burrows were being formed by, but nevertheless, it created what we can see in the Harefield pit. And as we move up through the time, as I say, we're trying to get through 2 million years every minute. We're up around 55 million years here, moving up towards the formation of the London clay. But before we get there, there's our Hertfordshire star coming in again. Conditions on land were pretty good. We're seeing mammals becoming established. It was warm. It was extremely warm. The chalk cliffs, as I say, we know that the chalk was being eroded. It wouldn't have looked like this. The present day chalk cliffs, they would have been eroded back. And we may have ended up with a sort of paleo environment, which was really reflecting subtropical conditions. I put a note in here around about 56.7 million years ago. Globally, it was really hot. When I say really hot, the Earth, for a period of around about 100,000 years, maybe less, went through a period not just climate change and global warming, but global temperatures really rocketed. They went way off scale. There's various explanations why this may have took place, but nobody's really 100% sure. But temperatures were so high, they affected the chemistry of groundwater, and these nice pebbly strand lines that we see developed in our part of southeast England ended up as this stuff. I think you'll probably know the Hertfordshire pudding stone. Basically, it's a pebbly conglomerate. It's what we call a silcrete, because even the matrix between the pebbles is being formed of silica. So the sand that was originally in here is basically altered to solid silica. And pudding stone is really well known. This is if you know the Waffle House, the Kingsbury Mill Waffle House in St. Albans, then this is a classic lump of pudding stone sitting outside. And other lumps immediately adjacent and in the local walls show you the sort of typical sort of pudding stone that we see developed. So this was formed around about 56.7 to 56 million years ago. Now, moving up slightly younger, 55 to 50 million years, there were sharks around. During the early Eocene, not like the ones that we get in present day Hertfordshire, but actually real sharks. This is the typical early Eocene London clay deposition. So Hertfordshire was back underwater again. On the margins of the London clay sea, the deep water area was still out in the North Sea rifting trough that was filling up with thick clay deposits, and in some areas thick sand deposits that would eventually become petroleum reservoir sands. But in Hertfordshire, we do have London clay deposits, and we find fossils that go with it. So we've been through the chalk, we've visited the tertiary, or the lower tertiary, the Paleocene and the Eocene. So we've gone up through this bit. We need to come up and maybe just stop over very briefly in the Pliocene. This is really, it's a little bit controversial. Some people won't believe it, but it's worth putting in just to bring it to your attention. Do we have Pliocene deposits in Hertfordshire? Well, there are some people, and I know Nick, who is standing here at Little Heath, is listening tonight. So Nick, I'm using you as scale. This is Little Heath at Berkhamsted. And these are supposedly marginal marine beach sands, or sands close to the beach somewhere. And they're sitting on top of Chiltern chalk, which is just underneath this sandpit. And it's regarded this could be the Hertfordshire equivalent of what we call the red crag, which are clays and sands across in Suffolk. The red crag is this brown level over to the east of this map. And you can see here's Little Heath sitting over on top of the chalk. We also have Rothamsted and Harpenden. And there were some red crag fossils recovered from Rothamsted, but some people argue that these are glacial deposits. But the late John Catt, who many of you will know from the talks that he's given to the Natural History Society, John was a great believer that Little Heath, in fact, represents Pliocene sands. And he organized dating of the sands because there's no fossils in it, there's no minerals we can date as such, but you can use cosmogenic dating, the amount of sunlight the sand has been exposed to. And the date that came back from that is around 2.57 million years, which would put us around about beach level in the Chilterns about 2.5 million years ago. Which means, if that's correct, that the Chilterns has risen by around about 165 meters over the last 2.5 million years. And it helps to account for that present day escarpment, the development of it. And you can see here the heights above sea level that Pliocene deposits were deposited or are found at today. And you can see them getting progressively higher onto the Chilterns in this map that John Catt produced back in 2010. So that's a quick visit to the Pliocene. It's just in passing, but it's there. We can't deny it's there. The sand exists. So we have to account for how it got there. So let's bring it much more up to date. We'll skip from the Pliocene and we'll come right up to around about 450,000 years ago, just less than 500,000 years. So it's getting really quite modern. So what have we got in Hertfordshire at that stage? Well, we're actually seeing evidence of major glaciation, major ice ages. And do we see mammoths? Well, we've got mammoth tusks across at College Lake. So we definitely had large mammals such as this around about the time when the Anglian Ice Age was affecting or coming through the Chiltern area. So that Ice Age, how did it impact what we see through the county? So where were we in time? This is if you like, the amount of CO2 and how it affects the temperature. And if we look, this peak through here, which is picked out by the red arrow here, is in Britain, the Anglian Ice Age. So it's around about 470 to 440, 430,000 years ago. And that ice age had a major impact on this region. If we look at the globe, ice caps swept right the way down into Europe, right the way down into North America. So major ice caps covering the region. If we come in detail and look at what was the situation around where we are, across Europe, we had this major ice sheet and it's blocked the outflow from the major rivers from the Scheldt and the Rhine and the Thames, the Proto-Thames, into the sea. In fact, it becomes a major ice dam lake, which eventually, when it overflows, takes out what was to become the English Channel. But what we're interested in is our bit of Hertfordshire and what was going on through here. And if you look carefully at this lowest green arrow, which is the line of the Proto-Thames, you can see that it's not coming out through the Thames estuary as we currently know it, but it's coming out further north through the lower part of East Anglia. And if we go back to pre-Anglian times, here we go, the Thames came up through the Vale of St. Albans, through Hatfield, across through Hertfordshire, and eventually made its way out to sea around about Clacton. Other tributaries, the Wey, the Wandle, came into it. The Medway even flowed across and joined with it. But then when we get the Anglian ice sheet, as you can see in this lower diagram, that ice sheet spread down way into the region of Hertfordshire and even towards London, down the Lee Valley. The Vale of St. Albans was blocked by ice. This was part of the Wear ice sheet coming through, and we have what is a huge lake developing along what is now the Colne Valley. If we look at this this is one of the BGS maps from back in the mid-90s. Here's that lake, and the lake, this is the original Proto-Thames, went up through Beaconsfield across into St. Albans. But then as it was dammed by ice, the lake built up, and effectively a sediment delta started to fill the lake. This formed all the gravels that we see in through the Colne Valley, which have been frequently done, formed the lakes as those were excavated. And the River Thames eventually flowed down into what would become the River Colne, and the Thames itself was diverted south through Maidenhead and then across past Slough onto its present day route. So Hertfordshire had got a major ice sheet with a lake building up, looking probably something, I won't say exactly like this, this is modern day equivalent, but at least it gives you an idea of the sort of geography we had sitting in Hertfordshire at the time. And the Vale of St. Albans that we know so well has been backfilled with loads of gravels that have been excavated through time, forming a lot of the gravel pits and lakes that we see running through from St. Albans, well, past St. Albans and up to Hatfield. So we had this major glacial lake that backed up right into, down into the Colne Valley. There was probably evidence of early man, but things haven't changed. I mean, the ice melted eventually, and here we go. Here's the message. Let's go down to the 6 bells. If the pub was open, things haven't changed too much. So that's the story of Hertfordshire through to the end of the Ice Age period. And it's always interesting if we play a little bit, we can look a little bit further into the futures, and we can use our time machine to shift forward a bit. And this is where it becomes a little bit tongue-in-cheek, but it's worth having a look at. I showed you this before when we were looking at the Anglian ice sheet and the Anglian glaciation down here. If we come through to the previous, if you like, warming period around about 120,000 years ago, this peak in carbon dioxide resulted in a 6.6 meter sea level rise. We are now going way off scale, heading towards 400 parts per million up here. So you can imagine the sea level rise is going to really start pushing quite high. If you do a total ice melt, and then you say, okay, say we had some thermal doming, a bit like we had in the late Cretaceous. I'm not saying they will, but sea levels could rise back to the 100-meter level. And with a 100-meter rise in sea level, you can see how much of the UK and Northern Europe starts to flood. and you end up with a situation looking a bit like this, or even a bit like this, which may be an improvement on things. I don't know. It depends on how you look at it. But it's certainly a situation we do have to think about. Because if we look at the map of the Chilterns as it currently stands, the Chiltern escarpment that we've been talking about through here, and we raise sea levels by about 90 meters, then you end up with a rather nice archipelago of islands reaching down towards where Goring once used to be, I guess. So perhaps we've ended up close to where we started. Safest place to buy your second home is probably in the Northwest Highlands of Scotland. If you look on the bright side, seaside would be a lot easier to get to. You wouldn't have to drive around the M25. And my home at St. Albans lies between about 85 and 100 meters of present sea level. So Fishpool Street would probably live up to its name. I will advertise this book. A lot of you may well have got copies. It says, according to the Hertfordshire Natural History Society website, it's out of print. Well, it may be out of print, but I've got spare copies. And if anybody wants a copy of this book, which is an absolute goldmine of information and a standard of its time, then get hold of my email and I will let you have a copy. Apart from that, thanks for listening. And if anybody's got any questions, I'd be only too pleased to try and answer. Thanks very much.
Haydon, thank you. That was fascinating. As somebody who lives not far outside St Albans, but at 140 meters, give or take, probably a bit more relieved, but probably not something I need to worry about in my lifetime. But global warming obviously is something we all need to worry about. In terms of the Hertfordshire geology book, actually, I think it's worth saying it's probably been, I think, our bestseller ever for the Natural History Society, and we've actually reprinted it a couple of times now. So, so demand continues to be good. I've certainly got the odd question, but let's just open the floor whether there's any others. I can't see any in chat. I'll keep half an eye out for raised hands, but just while there is a couple from me, if I may. Flint, I always think of chalk and I think of flint. You mentioned Hertfordshire pudding stone. Is flint again one of these stones that's been formed out of the burrows? So yeah, how does it? What's the relationship there?
Okay, I could give you a whole talk on flint formation. Yes, let's try and simplify it really closely. First of all, you've got to get a supply of silica, and the most obvious supply of silica in the chalk were those sponges that we kept on coming across as we went through the chalk. Sponges have skeletons made of silica, and when the chalk was being buried and going deeper, that silica went into solution and became part of, if you like, the formation water. It's then a matter of crystallizing out that silica, and back in the 1980s, a guy called Chris Clayton did his PhD on flint formation. And for the first time, Chris came up with he's a geochemist. He looked at the chemical controls on silica crystallization. And what he found was that where you got within the sediment, you would get oxygenated circulation of oxygen in the upper part of the sediment. But in the lower part of the sediment, you would get bacteria which are living in an anoxic environment. You get a reducing environment. And where the boundary is between the oxic level and the anoxic level, that's a redox boundary, then that is the sort of environment where silica crystallizes. And what Chris also found was that where you had previously had biological activity, so burrowing is a classic example, where that burrowing had taken place, that provided sites for crystallization. So the typical flints that we find in the white chalk are, the vast majority of them are following what we call thalassinoides burrows. but there are other types of burrows within the chalk, and those burrows were created by other organisms. They're feeding traces, things we call zoophycos, another one called chondrites. Wherever we get these different types of trace fossils, then frequently flint will form following the lines of those fossils. It forms in other places where there are bits of paleontological remains. So you find silicified echinoids. We all are picking up micrastas that have been formed or replaced by flint. So yeah, flint is one of those, it's a strange rock. It forms relatively early in the burial of the chalk. And once it's established and hardens off, then it's difficult to get rid of, as you will well know when you try and garden it around here. So yeah, but if anybody, as I say, that could have been one of the other talks we could have had, or part of the deposition of the chalk. But yeah, fascinating material and very closely related to the biological activity that we see within the chalk sediments.
Excellent, thank you. Really helpful. I see there's a question in the chat from Julia Battersby. Are there many sinkholes in the Hertfordshire chalk?
There are far too many. We tend to hear about the ones that get into the local papers, like the one in Hemel Hempstead and the other one at Hatfield that I can think of, and the one in St. Albans. I can give you an example. When we were writing the Hertfordshire geology book, I suggested to John Catt that we contact a guy called Clive Edmonds, who was a specialist in sinkholes. And I asked Clive if he would write a section of the Hertfordshire geology book about the sinkholes in the county. And these also, a lot of the holes in the chalk are also, there are chalk mines, which are man-made. So I approached Clive and said, look, I know of about 7 or 8 mines, chalk mines in the county, and a few sinkholes. Would you mind writing it up? And he then said to me, you do realize there's at least 150. So yes, there are plenty of sinkholes in the Hertfordshire chalk. They occur very, very naturally. A lot of them tend to follow structures in the chalk where there's faulting and where periglacial activity has opened up solution pipes that they've followed. Some of them have been impacted and created by human activity, particularly brick making. So if you've got old brick pits in the area, the brick would have come from the clay sitting on top of the chalk, but it was normal to mix around about 10–15% chalk with the clay mix so that the bricks didn't crack when they were fired. So by digging through the clay into the chalk, the brick makers opened up passages for water to seep through the overlying clays, which makes the water acidic. And of course, as soon as the water gets into the chalk underneath, because it's acidic, it starts to dissolve away the chalk, and you get effectively what is a karst topography, like we used to in limestone scenery. And it's one of the things that the mapping that the BGS have done over the last 5–6 years is to recognize that what we're dealing with in the Chiltern area and the chalk area is effectively a karst scenery, similar to what you would have in the Peak District on the Carboniferous limestones, but here it's on top of soft chalk, and that's going to open up major holes. So yeah, always be aware of it in this area. It's going to be there are going to be features where you are living on the chalk, or if there is a thin layer of clay on top, then you may have sinkholes developing underneath. Sorry to worry you on that one, but yeah, it's unfortunately true.
Yeah, it's certainly a feature around where I am that you've got quite a few of the fields have quite big pits in them where they look as if they've been dug for chalk for presumably fertilizer or something at some point in the time. Yeah. Bill, you wanted to come in?
Yes, a quick question. You've covered pudding stones, which you get in this part of the sort of chalk landscape. I come originally from Wiltshire, the Marlborough Downs, and the stones that you find there are the sarsen stones, which seem quite similar, but they're a much finer one. Can you explain that?
Yeah, they are directly comparable in age with the pudding stone that we get in this region, but they formed basically they're formed of a fine sand. Although we're used to seeing these what is a typical flint conglomerate which forms pudding stone. If you actually, there's at least one location in Hertfordshire near to Radlett where you can actually see pudding stone in situ, but it's one of these places that everybody's sworn to secrecy where it is. So if we take you in there, we actually kill you on the way out. But you can actually see how the pudding stone goes into a soft conglomerate with pebbles, but with sand in it. And another good example, one that you can go and see, and again, Nick Pierpoint is in the audience tonight. Nick has organized information boards, information stands with. If you go to Castle Hill in Berkhamsted, on the roadside verge on Castle Hill, there are some lovely lumps of pudding stone. But if you look at one of them, half the block, and these are big blocks, is effectively a sarsen stone. It's a fine sand. So it's it's really just a matter of the grain size of the material that was present. And in the Marlborough Downs area, those sands or the sediments would have been fine sands rather than the coarse material that we have in this part of the world. So when they silicified in those large blocks, which we now know as sarsen stones. But effectively, they are time equivalents of the pudding stone that we have in this part of the country.
Okay, thank you very much.
Yeah.
Excellent, thank you. Any other questions for Haydon from anybody? I can't see any more in the chat. Anyone else want to come in? No? In which case, I think we'll probably wrap up there. Thank you very much, Haydon. That was fascinating. As a local resident for many years, it's just really interesting to understand a bit more about the geology under our feet, and particularly living very close to the M1 and having seen all the excavations and the various pipes, you get to see some of these layers as they work through. It's fascinating to find out more. So thank you. And judging by the comments in the chat as well, a lot of colleagues found equally fascinated. So huge thank you to you. Thank you to Tim Hill for organising this evening, and for Dan for hosting us on Zoom, and to everybody from both the Welling Natural History Society, Hertfordshire Natural History Society, and indeed colleagues from Geological Society as well. Thank you very much. Thank you everybody for joining. Haydon, again, thank you very much.